Hi everyone, welcome back to Physics 11. So I wanted to go over some of the questions that some of you asked me to go over from the thermal energy worksheet. So question number 3 says we have 0.240 kilogram chunk of carbon that's heated to 215 degrees Celsius and quickly placed into 0.275 kilogram of water that has an initial temperature of 12 degrees. What will the final temperature of the water be? So here's what we know. We know the initial temperature of the carbon, 215. We know the initial temperature of the water is 12 degrees. We don't know the final temperature of either one. We know the specific heat for each one. So carbon is 720 joules per kilogram Celsius and water is 4,180 joules per kilogram Celsius. And we also know the mass for each one, so for the carbon and for the water. So initially, of course, the carbon is at much higher temperature compared to the water. Once you dunk it into the water and you leave it sitting there, we know that the gradient is always going to go from high to low. So the carbon is going to give up some of that heat to the water, which means that the temperature eventually will equalize, will become the same for both of them. So even though we don't know the final temperature, we know that it will be the same for both of them because once you leave it, the system will reach an equilibrium. So eventually this will be the same. And that's really important because otherwise we can't really solve this question. So we had to realize the fact that the final temperature for both of these types of materials, water and carbon, will be the same. So how do you solve this question? So if you think back to just potential and kinetic energy, if you had changes in kinetic, that means that the energy is going to get transferred into potential energy. So if you remember, we had delta EK is going to equal a change in potential energy. Now, if one is increasing, the other one is decreasing. So we had to put a negative sign to one of these, right? So either kinetic or potential, depending which one is increasing and which one is decreasing. Because when you move this to the other side, okay, they should add to zero. So anyway, we're going to apply the same principle, but because we're not dealing with kinetic energy or potential energy, we're dealing with thermal energy. Instead of delta EK and delta EP, we're just going to have delta, let me use a different color, we're going to have delta E thermal, or heat. Okay. Now in this case, we have two different materials, so we're going to have two different ones. So let's say carbon and delta H2O. So it's more clear which one's which. Now again, one of these has to be negative. Doesn't matter where you stick the negative as long as one of them is negative. So this is the one we're going to use here. So again, the same principle, conservation of energy, applies. Instead of dealing with gravitational potential energy and kinetic energy, now we're just dealing with thermal energy. So let's try this out. For the carbon, we're going to have our, remember, our Q, or in this case we're using delta E equal to mc delta capital T for temperature. So that's what the equation we're going to use. So again, instead of Q, we're using the change in energy because here we're just talking about changes in energy, but it's still the same equation. So for carbon, we're going to have our mass for carbon, or mass of the carbon, the specific heat for carbon, so C subscript C, and then the change in temperature for carbon equal to negative. Now make sure you put a parentheses in front of this and essentially use the same equation, but now just use different subscript. You can use 1, 2 for both of them. Here I'm trying to use a little bit more explicit subscript so it's easier to follow. So we have the mass of the water, we have the specific heat of the water, so CH2O here, and we have the delta T of the water, H2O. Okay? Now let's expand our delta T because that's the one that contains the final temperature that we're interested in. So let's write this one more time. MC Remember, delta just means final minus initial. So here we're going to have our T final. And T final is going to be the same for both of them. So I'm not going to write a subscript because it's going to be the same T final for both of these materials. Minus Ti carbon. I will use a subscript here. Equal to negative parentheses mass of the water, specific heat of the water, times, again, T final. I'm not going to use a subscript because it's going to be the same as the other, because that's what I'm going to try to solve for, and minus the T initial of the water, so TiH2O. Close all the brackets here. Okay, so that's what we have. What we're looking for is the T final, and we know everything else. We know the masses, we know the specific heat capacities, we know the initial temperatures. So it's really just a matter of doing some algebra here. It's not a very complicated question. As long as you know what you're starting with, if you get this equation right, everything else is just mechanics, right? It's just going through the algebra steps. So, all right, let's go through the algebra steps. We can drop one of the parentheses here on the right side. So let's do that. And what else can we do here? We'll have to FOIL this out. So we'll have to multiply MC times the T final and then MC times the initial temperature for both of them, and eventually put all the T finals together. It's just a lot of algebra steps, but that's what we got to do. So MC times CC times this guy is going to be T final minus MCCC times Ti for carbon. So that's our left side. On the right side, we're going to have a negative MH2O CH2O times the T final, so TF. Now here, because this whole thing is negative, if you remove this set of parentheses, basically doesn't really change anything, we just remove them. We're gonna end up with negative times negative once you FOIL the next part. So we multiply this times this, then multiply this times that, so negative times negative becomes positive. Mass times the specific heat of water times the initial temperature, TiH2O. All right. So again, we're looking for the T final right here. Now the reason we have to expand is because we need to put all the T finals together in order to solve for it. So you can move the terms with T final to one side, move the other term to the other side. So I'm going to move the this guy here to the left, and I will move this term to the right. Sorry, the other way around. The red one will move to the right, the green one will move to the left. So let's do that. So the mass of carbon, specific heat of carbon times the final temperature plus the mass of water, H2O, times the specific heat of water, H2O, times the final temperature. Okay, that's on that side. Now once you move this becomes positive, so we have the mass of carbon times specific heat of carbon times the initial temperature of carbon, which is positive now, plus the mass of water times the specific heat of water times the initial temperature of water. All right. So on the left side, we can factor out the final temperature. So you're going to factor the TF. No equal, sorry. There should be parentheses. So we factor that out, and we get the following expression. Now I do realize it will look a little simpler in the key because I'm not using the subscripts H2O and C, so it looks a little easier there. But again, this is just to keep track of things a little bit more. So on this side, we can leave it as is. There's nothing that we can factor on the right side because all of these are different variables. There's nothing in common. So we're just going to leave it alone. Okay. So the next step is now get the TF by itself, which means we need to divide by this term that's in parentheses to get the TF by itself. So the T final is gonna equal all the stuff that's on the right side divided by the stuff that's on the left here, so we get this. So we have the mass of the carbon times the specific heat of carbon times the temperature, initial temperature of carbon. Then we have the mass of the water, H2O here, times the specific heat of water times the initial temperature of water over MCCC plus MH2O times C subscript H2O. All right, and that's going to be our expression for the final temperature. So we have our equation written down. The next step is to substitute in all of the values. So let's substitute the values. So let's plug in the value for the mass of the carbon, which was 0.240. Specific heat of carbon, which is 720. Initial temperature of carbon was 215. Plus the mass of the water, which is 0.275 times specific heat of water, which is, again, it's written up here, 4180. And what else? The initial temperature was 12 degrees, I believe, 12. Okay, so all of this over the mass of the carbon, which is again 0.240 times the specific heat of carbon, which is 720, plus the mass of the water times the specific heat of water. Okay, so that's going to be our final temperature. And again, you can do this on the calculator, all the calculations. If you're going to do this in one go, I suggest you add a couple more brackets around this. So maybe bracket there, and then you can do all of this divided by all of that. If you want to do this in one go on the calculator, so let me just punch this in. So for the top, for the numerator, so far, this is just an intermediate step, so you can kind of check where you are. So far I got 50,946. Let me do the bottom, the denominator, see what I get. So at the bottom I got 1,322.3. So let's divide these two together. So 50,946 divided by that, I got 38.53 degrees Celsius. So that's going to be our final temperature that both the water and the carbon is going to be once they reach equilibrium. So the last thing left to do here is just figure out the number of sig figs. So for the top we have multiplication and addition. So for the multiplication part, you should end up with 3 sig figs in the first term, 2 sig figs in the second term, the numerator. So that probably going to leave you with, once you add them, it's going to leave you with the same number of decimals. Well, let's double check. 0.24 times 720 times 215. So that's going to leave us with no decimal in the first term. 0.275 times 4180. So no decimals. So when you add them, you should end up with no decimals, which basically you end up with 2 suffix on the top. So that should be 2 suffix there. And then at the bottom, looks like you should end up with 3 suffix because both of these are going to have same number of decimals. But because we have 2 suffixes on top, we have to round this to 2 suffix as our final answer. So we're going to end up with, round it up, so we end up with 39 degrees. So basically, the temperature of the water and the carbon is going to be 39 degrees Celsius.